Good morning, everyone. My name is Kelly Tiokai. I'm from Group 3, number metric TB21027. Now I will represent the project, which is Design and Analysis between Amplitude and Frequency Receiver. In this project, we focus on the design, simulation, and analysis of amplitude modulation communication system, and the implementation in the two types of transmitter. First one is high level, second is the low level transmitter. And we have two types of receiver also, which is tuned radio frequency TRF receiver and direct detection receiver. And the carrier that we focus is 444 kHz, and the modulating signal is 4.4 kHz. Next, for the transmission design, the high-level transmitter, the modulation state need to in the final power application stage. However, for the low-level transmitter is in the early stage before the power amplification. Then the amplifier that used for the high level is Class C amplifier. Then for the low level is Class A or Class B. The power efficiency of high level transmitter is high compared to the low level transmitter. For the complexity, the high level is more complex than the low level. For the application for the high level is can use on the broadcasting and long distance communication. But for the low level transmitter is in the short range communication system. Next, for the tuned radio frequency receiver, this is the block diagram of the TRF receiver. The tuned radio frequency is one of the early designs used in the radio communication. It's operated by directly amplify the received radio frequency signal using the multiple tuned RF stage. Each stage is tuned to the same frequency as the incoming signal, and the amplifier signal is then demodulated to extract the original audio or information. Then, the component inside the block diagram, the RF amplifier is amplify the received signal. Tuned circle select the desired frequency. Detector is the demodulator that demodulate the signal to recover the original information. Audio amplifier is used to boost the demodulated signal for the output. The second one receiver that I will use is direct detection receiver. This is the block diagram. This receiver employs a direct diode-based envelope detector to demodulate the AM signal. It's also known as a non-coherence receiver because it does not require synchronization with the transmitter's carrier signal to demodulate the received signal. Instead, it direct extract the modulated signal from the incoming AM waveform using a simple demodulation technique, such as envelope detection. The component inside the block diagram, the first one, the important one, is recover, extracting the original transmitter signal from the received optical signal. The telescope focus and complement the outgoing transmitter and collect the receive. For the photo detector, convert incoming optical signal into the electrical signal. Amplifier is also used to boost the signal. Then for the processor, recorder the amplifier electrical signal and perform the error correcting and convert it into digital data or usable output such as audio signal. Optical filter is used to block the unwanted noise. Next, I pass to the member. Thank you.
Everyone, my name is Nurhazika, TB21025, and we will be discussing the analysis of an AM transmitter and receiver system. So we'll cover three components, which is the low-level transmitter, the TRF receiver, and the envelope detector. So for the first is the low-level transmitter, which is this section generates an AM signal by combining a high-frequency carrier with a modulating signal. So here we can see the oscillator. In this stage, which is it generates a stable high-frequency carrier signal. So we can see that L1 and L3 here is the LC tank circuit, which is to ensure the oscillation at the desired frequency by filtering what we unwanted harmonic. So here is the C5 act as a coupling capacitor to block DC component while transferring the AC signal. Next is the modulator. The function is to combine the carrier modulating signals to produce an AM signal, and which is another LC circuit, which is L2 and C9 filters. The modulated signals is to maintain the stability. So the C10 is the couples AC component to reduce the noise. So here we can see the filters also, which is in this transmitter, it ensures carrier frequency, which is to clean and free from interference, providing selectivities and reducing the distortion. Below here, we can see the TRF receiver, which is designed to amplify and recover the transmitted AM signal. So we can see the RF amplifier, which is tuned LC circuit is pairing. So in this LC circuit, selected the desired carrier frequency and reject others by providing strong selectivity and amplification of the signal. So here is the tune circuit, which is each of RF stage, we have each tune circuit. So we can amplify only to the target signal by filtering out the adjacent frequency. And then below here also, we can see the envelope detector, which is to extract the original modulating signal. And up then, we can see the audio amplifier. So audio amplifier is to recover the audio signal that is sent to increase the volume for output through the speaker or headphone, as we know. So back to the envelope detector, you can see here, you can see diode and RC network. So this diode only allows one polarity, which is positive half cycle of the AM signal to pass rectifying the signal. And this type isolates the amplitude variation, which corresponds to the originality modulation signal. So RC network is for smoothing circuit. Okay, this capacitor charged to the peak voltage and then rectified signal and discharged slowly through the R resistor. And this breaks the envelope signal while filtering out the high frequency carrier. So this is what we call as demodulation process. And the envelope corresponds to the original modulation signal, which is then amplified by the audio amplifier. So this method ensures the recovery of a clean low frequency audio signal.
My name is Muhammad Faridudin bin Muhammad Ilyas, IDTG 12037. So today I will present about high level AM modulation transistor is an amplitude modulation that achieve optimal signal fidelity, efficiency, and robustness. This is the direct detection circuit receiver. So direct detection a modulation receiver is a simple type of a receiver designed to demodulate amplitude modulation signal by directly extracting the modulated signal. And this is the product detector. Product detector is operate on the principle of mixing, where the modulated signal is multiplied by locally generated carry signal. So this is the modulated signal for the circuit, and this is for the demodulated signal for the circuit. So as you can see, and this is the mixing of the two signal. So this we got 1.2 volt, and this we got millivolt. So the gain for this product is not the same with the calculation, because uh, the noise and the tolerance of the circuit is very different from the value of the result that display here. So everything, the bandwidth also different, same. So the modulation index also different, and the power efficiency also different. It's not the same. So I think that's all from me. Thank you.
Hi, my name is Aina Nadira, and I will discuss about the final result analysis on both of the simulation output for this project. For the first simulation at a low level, at the transmitter output, the modulated signal has a 10.4 Vp to peak, amplitude of 5.2 V. Meaning for the Vp to peak matches the expected output, because Vp to peak is equal to V max minus V min, where 10 V minus 0 is equal to 10 Vp to peak. And the frequency observed is 8.8 kHz. The sideband should be at 439.6 kHz and 448.4 kHz, representing the 44.4 kHz modulated signal. At the receiver output, the demodulated signal frequency is 89.5 kHz, amplitude of 487.7 Vp to peak. This result might due to the oral amplification, noise, harmonics, and distortion. Next, these are the figures for distortion and noise that are found in the demodulated signal. Output clarity for simulation 1, the demodulated signal mismatched the original modulating signal in terms of waveform shape for its amplitude and frequency. These are the calculations for gain, audio amplifier, bandwidth. Gain at RF amplifier is 3.55. Audio amplifier has a gain of 4. Bandwidth is 79.63 kHz. And the modulation index is equal to 1. Power efficiency is 33.33%. Next, for the analysis on result simulation 2. At the transmitter output, the modulated signal has a 700 mV amplitude, Vp to peak of 1.4 to V measured, frequency of 444 kHz. The sidebands are representing the 4.4 kHz modulating signal. And at the receiver output, the signal has a frequency of 4.4 kHz, which is the original modulating signal. We have the amplitude of 1.14 V, and the Vp to peak is 2.28 V. These are the frequency spectrum by using the spectrum analyzer with the cursor showing at the center for the frequency 444 kHz and the sidebands at the modulated output and the modulated output. This is showing the SNR calculation for finding whether the signal power is more than the noise power, which is the noise level, showing the signal is on a good ratio. The noise are found at the demodulated signal with a positive of 21.209 dB. Is indeed showing the signal could overcome the noise level that occurs in the demodulated signal. For output clarity estimation 2, the demodulated signal matches the original modulating signal in terms of the waveform shape for its frequency, which is 4.4 kHz, and the Vp to peak measure is 2.82 Vp to peak, making the amplitude Vmax at 1.41 V. These are the calculations for the high level. The gain, which is negative 431.37, and bandwidth 117.90 kHz. Modulation index of 1, power efficiency with 33.33%. That's all for my part. Thank you.